Evaluate limits analytically for functions with essential discontinuities. Alright, so in this video we're going to be talking about infinite limits, what they are, and how to evaluate them. So let's first start by looking at the limit as x approaches 0 of 1 over x squared. And we know that our first strategy that we should always try with limits is direct substitution. So we'll just go ahead and we'll substitute in directly. And we see that x is approaching 0, so that means we will substitute in 0 for x to get 1 over 0 squared, which is going to be 1 over 0. And, what does that mean? We get 1 over 0. And if we think back to math, well, 1 over 0 is an undefined number. It's an undefined expression. We can't take 1 over 0. And that's true, but that's only true when we're talking about actual values. Remember, here we're talking about limits. So we'd actually never end up with the fraction 1 over 0. That's just the values, that's just the numerator and denominator that this limit is approaching. So, while this is not undefined because it's not an actual height, it still does put us in a little bit of a predicament, because what do we do now? We know that when we have 0 over 0, we can factor and cancel. But 1 over 0, So, why don't we go ahead and let's look at this from a graphical approach. So if we were to take a look at the graph of this particular function, we would see here that something special or something different is happening as x approaches 0. So here we can go ahead and we can look at our individual one-sided limits. So we'll take a look at the limit as x approaches 0 from the left, and the limit as x approaches 0 from the right. So limit as x approaches 0 from the left of f of x, and then we'll do the same thing. We'll take the limit as x approaches 0 from the right of f of x. Now, looking at our graph, if we are looking as x approaches 0 from the left-hand side, so as we get closer and closer and closer to x equals 0, we want to look at what the height does. How does this function behave? As we can see here, the function increases. It increases dramatically, and then it's almost essentially a vertical line. And as we can see here, that this particular function goes up and up and up and up and up forever and ever and ever. So, if we're trying to kind of quantify that up and up and up forever and ever and ever, find some way to identify the height here, well, we would say that the height is always increasing. So the height is always getting higher and higher and higher, and it goes on forever. So the limit as x approaches 0 from the left of f of x, we would say equals infinity, because infinity means the number keeps getting larger and larger and larger, just like our height of the function as we approach from the left. And then we can do a similar thing for the right. If we look as our x value gets closer and closer and closer to 0 from the right-hand side, we can see that our function, the height of our function, keeps growing higher and getting larger and getting further away from the x-axis, and it goes on up forever and ever and ever. So therefore we could say that the limit from the right, in this case, also equals infinity. Alright, so each of these one-sided limits approach infinity, and this is not something that we've dealt with in calculus before, but it's something we're going to introduce right now. But before we move on, we can see here the limit from the left equals infinity, and the limit from the right equals infinity. However, we can see here that our lines don't meet at any particular point. So one of the questions we will have to answer is, does the two-sided limit exist? And again, we will come back to that once we do a little bit of defining. So what is an infinite limit? Well, an infinite limit or infinite limits occur when function values increase or decrease without bound near a point. And that makes a lot of sense except for this whole, without bound terminology. Like, what does that whole without bound mean? Well, mathematically speaking, that means there are no boundaries. There are no limitations to how much or how high a value can increase, or how farther down or farther away from the x-axis a number can increase. So when we're talking about without bound, we're referring to either infinity or negative infinity. So basically, infinite limits occur when function values increase or decrease to positive or negative infinity. And just to put that a little bit better, infinite limits occur when the intended height goes to positive or negative infinity. So let's take a look at how we might expect to see some of these graphs that approach infinity. So first off, if we look at this particular graph, we can see that this particular graph approaches infinity from the left-hand side. And just like before, we can see that as our x values approach some a value, our y values or our height get larger and larger and larger and continue to infinity. So one would say that this is one possible graph that we might see for a left-sided limit that ends up equaling infinity. Now if we look at another left-sided graph, we might also expect to see a picture like this when we are looking for a limit that approaches a from the left-hand side. And as we can see in this particular graph, that as we get closer and closer to our a value, this particular function gets closer and closer to negative infinity. So this is an example of a shape of a graph that gives us a negative infinity as we approach from the left-hand side. Alright, now we can look at our right-sided limits. So we can see here that we might expect a picture that looks like this. So we're going to be approaching a from the right-hand side. And just like the other two, as we get closer and closer to our a value from the right, our limit gets closer and closer to infinity. And then our last potential shape here, as we approach a from the right-hand side, would look like this particular graph. And just as the other three, as x gets closer and closer to that a value, as we can see, this particular graph gets closer and closer, or gets farther away from the x-axis in the negative direction, which means it gets closer and closer to infinity. So returning to the last question we talked about in our first example, when do infinite limits exist? Just because one side equals infinity and the other side equals infinity, does that mean that the two-sided limit equals infinity? And in this case, it does, yes. The limit as x approaches a of f of x exists when both sides approach infinity, or when we have a graph that looks like so. So yes, technically, the limit does exist because, remember, the limit is the intended height, and since they're both approaching the same intended height, we consider it to exist, and it exists at infinity. But there will be no actual height because infinity is not an actual number. Similarly, the limit as x approaches a of f of x exists when both sides approach negative infinity, so a similar situation here. That when both sides are both getting farther and farther and farther away from the x-axis in the negative direction, we can say that the two-sided limit approaches an infinite value, in this case, negative infinity. Now, when we do get the case where one side goes towards positive infinity and one side goes towards negative infinity, that's when we say the limit does not exist. So, the limit as x approaches a of f of x does not exist when both sides approach different infinities. Alright, so going back to our first example, we can now finally answer this question. Since the limit from the left and the limit from the right both go towards positive infinity, we can say that this two-sided limit exists and that it does in fact equal infinity. Alright, so next up we're going to take a look at determining infinite limits graphically. In this example, I want to use the following graph to analyze the following limits. And the graph we're given is the graph of the function f of x is equal to x over the quantity x squared minus 1 squared. Alright, so let's see, our first limit has the limit as x approaches negative 1 from the left. So first let's identify this x value. And as we can see, the x equals negative 1 is right here at our vertical asymptote. And we are approaching negative 1 from the left-hand side, so starting out from the left-hand side of this graph, we will follow this graph and see what happens to the height as we get closer and closer and closer to x equals negative 1 from the left. And as we can see here, as we get closer and closer to negative 1 from the left, our function is getting farther and farther away from the x-axis in the negative direction, meaning that it's going to give us an intended height of negative infinity. Next up, for number 2, we're looking at the limit as x approaches -1 from the right. So starting on the right-hand side, we can come on down, and it looks as though this trend is the same thing. As we approach -1 from the right, we do approach -infinity. Now, since our limit from the left is the same as our limit from the right, kind of, sort of, it is in terms of our definition of infinite limits, therefore the two-sided limit is going to equal -infinity as well. All right, moving on to number 4, we want to take a look at the limit as x approaches +1 from the left. So first, let's identify x equals +1, and we have our vertical asymptote here. And when we approach 1 from the left-hand side, it appears as though our function keeps going up and up and up and up and up. So therefore, we know that this limit is going to be +infinity. Next up, number 5, limit as x approaches 1 from the right. So starting on the right-hand side, we will continue to follow that as we get closer and closer and closer to 1. And this limit also appears to go to infinity. So, since the limit from the left and the limit from the right both appear to approach infinity, we say that this two-sided limit is going to approach infinity as well. Alright, so let's take a look at another example here. Here we have the limit as x approaches 1 from the left of g of x, and we're given our g of x function as the quantity x minus 2 over the quantity x minus 1 squared times the quantity x minus 3. So, let's first identify the line x equals 1. That can be found at our vertical asymptote at x equals 1. Now, when we're approaching 1 from the left-hand side, we can see that the behavior of this graph as we get closer and closer to 1 is going to continue to approach +infinity. Then for number 2, when we approach 1 from the right-hand side, we can see that this limit also approaches infinity. So therefore, the two-sided limit for number 3 will also equal infinity. Now moving on to number 4, looking at the limit as x approaches 3 from the left. So here is x equals 3. And if we're approaching it from the left, we're looking at it from this particular side here. And we can see that this limit goes towards -infinity. And for number 5, we're approaching 3 from the right. So from the right-hand side, we'll be approaching, looks like, infinity. So here we have a case where the limit from the left does not equal the limit from the right with infinite limits because they do equal different infinities. So in this particular case, the limit does not exist. Next up, we're going to be taking a look at determining infinite limits numerically. So we have discussed limits that are undefined. And so far we have discussed two numerical outcomes which lead to an undefined limit, with that first numerical outcome being 0 over 0. And we know that when we have a limit that approaches 0 over 0, that tells us that we can factor and cancel something out. The second type of undefined limit we've talked about is when we have a number over infinity. And we have already said that this is going to be an infinite limit, and it's going to equal positive or negative infinity. But without a graph, how do we figure this out? So, what about this case? What do we do when we get a number over infinity? We're going to demonstrate that by looking at the following example. The limit as x approaches 3 of 2 minus 5x over x minus 3. Now, we do always want to do direct substitution first just to see what's going to happen. So if we plug in 3, we're going to get 2 minus 5 times 3 over 3 minus 3, which is going to give us negative 13 over 0. Now, we do know that this is going to equal either positive or negative infinity, but we don't know which one. So, when we do end up with a number over infinity, we now are about to find out that our only option is to use a table. So, we are going to have to go ahead and we're going to have to split this particular limit up. And we're going to have to take a look at the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. So we're going to have to analyze each side of the two-sided limit, and we're going to be doing that by using a table. All right, so for our left-hand limit, we'll have our table x and f of x. And my input values are going to be 2.9, 2.99, 2.999. And then for the right side of the limit, we're also going to have x and f of x. And then our input values will be 3.1, 3.01, and 3.001. All right, so now I'm going to plug these inputs into my calculator to figure out what these outputs are. And let's see, when I substitute in 2.9, I'm going to get an output of 125. When I plug in 2.99, I'm going to get 1,295. And when I input 2.999, I'm going to get 12,995. So for this particular table, as our x values get closer and closer and closer to 3, we could see that our output values get closer and closer and closer to infinity. So therefore, the limit from the left will equal infinity. Now moving on to the limit from the right, when I plug in 3.1, I'm going to get negative 135. When I plug in 3.01, I'm going to get negative 1,305. And when I plug in 3.001, I'm going to get negative 13,005. So for this one, as we get closer and closer and closer to 3 from the right, it does appear as though the behavior of the function is approaching negative infinity. So therefore, our limit from the right is going to be negative infinity. Now, before we actually go ahead and evaluate our two-sided limit, I just want to point out one thing here. Some students like to just plug in one value and figure out like, oh, I got 125, so that's going to be a positive infinity, or 3.1, and oh, it's a negative 135, so therefore I'm going to get negative infinity. And while that might be true most of the time, we do know that there are some weirdo functions in math, and this will not always work out nice and neat like that. So that's why, if you notice here, I always chose to input 3 different values to make sure that I was able to definitively see a pattern. Because there are some of those outliers out there where just looking at one input won't give you enough information about the problem. So, rule of thumb is to please use 3 inputs when you use these table features. Now with that being said, we can go in and we can evaluate our two-sided limit, going back to our original problem of the limit as x approaches 3 of 2 minus 5x all over x minus 3. And since the limit from the left and the limit from the right go to different infinities, this particular two-sided limit will not exist. All right, for our next example, we want to evaluate the limit as x approaches negative 4 from the right of negative x cubed plus 5x squared minus 6x all over negative x cubed minus 4x squared. All right, so here we have a one-sided limit, which means we're probably only going to need to use one table. However, just to make certain that the table is what we're going to want to use, we need to use direct substitution to make sure we are going to get a number over infinity. Now, since this is the infinite limits video, we're going to get it. But shh, we should always check. All right, so that means we're going to have negative 4 cubed plus 5 times negative 4 squared minus 6 times negative 4 all over negative 4 cubed minus 4 times negative 4 squared. And now when we evaluate the numerator, we are going to get 168. And when we evaluate the denominator, we can get 0, which gives us the number over 0 case, meaning we're going to get some sort of infinity. Now, we just need to figure out which infinity, and we need to figure out which infinity when we approach it from the right-hand side. So we'll come over here and we'll set up our table, x and f of x. And since we're approaching negative 4 from the right-hand side, we're going to have inputs of negative 3.9, negative 3.99, and negative 3.999. Now the negative numbers are a little bit tricky by picking from the left and from the right, so I always recommend using a table just to make sure. So if we have negative 4, negative 3.9 would be on this side, and negative 4.1 would be on that side. Meaning, if we were approaching from the left, we want to use negative 4.1. However, in this case, we are approaching from the right, meaning we're going to use the negative 3.9s. Now, when we do input these into our calculator, negative 3.9 is going to give me an output of negative 104.4. And negative 3.99 is going to give me an output of negative 1,049. And then an input of negative 3.999 is going to give me an output of negative 10,499. And we can see here, as we approach negative 4 from the right, our outputs do appear to be approaching negative infinity, which means our limit as x approaches negative 4 from the right of negative x cubed plus 5x squared minus 6x all over negative x cubed minus 4x squared is going to be negative infinity. Alright, so just a quick review of what we do when we try to evaluate limits that have a denominator of 0. So, again, our first case was when we had a limit that gives us a 0 over 0. And when we get a 0 over 0, that means that we can factor something out and we can cancel. And typically, factoring and canceling, if we can remember back to pre-calculus, means that we have a hole in the graph at x equals a. The second case that we just talked about in this lesson is going to be the limit when f of x, let's try that again. The second, I just lost my train of thought. The second instance of getting a denominator of 0 is when we have a number over 0. And we know this is an infinite limit. So we know that this is going to approach one of the infinities. We just need to check the one-sided limits using a table to figure out which infinity this goes to. And as we saw from the graphical portion of this, when we do get a number over infinity, that implies that we're going to have a vertical asymptote at x equals a.